Hi everyone, and welcome to the final lecture of the winter semester before the Christmas holidays. Today, Tim and I will be joining forces to introduce you to a very interesting topic that some of you, if not most of you, have already been looking forward to, namely artificial neural networks. So the way we're doing this is I'm going to do most of the narrating part, and Tim is going to ask instructive questions to help guide along the lecture. And so as far as the topics are concerned, we're going to do this as a two-part lecture. So in the second part of this lecture is going to be after the Christmas holidays. And today we're going to talk about perceptrons and multi-layer perceptrons.
So I'm going to take the role of a student, which, by the way, is a little bit of a tradition. So every year I ask, my PhD students at least once to take over a lecture. And then I sneak in, like the lecture hall. And, I really enjoy it. I'm not doing this, to put pressure on you.
No, not feeling
maybe a little bit, but it's a good change of pace, changing the sides to see how this actually is perceived. And now, with this pandemic in full rage, and with us having to go back to video chat mode and stuff, I think this is also an experiment here.
Yeah, for sure.
We don't know if this works and if the students will like watching us, but I think we should test it. We should just find out,
Yeah, so I guess fingers crossed then. Hope they don't hate us after this experiment.
And maybe after the final exam, but
yeah, no, they can also take revenge in the evaluation at the end of the semester.
Yeah, they can, yeah. No, they won't.
All right, so
let's continue this thing here.
Yeah, all right. So so what I was going to say is that so just a quick heads up for you guys. This perceptron is going to be very familiar, or it's going to look fairly familiar to you at some points. And the reason for this is that the perceptron was developed in 1958 by Frank Rosenblatt. So it's a really old concept in machine learning. And what's really interesting here is that it was developed almost at the same time as logistic regression. And in fact, it bears a lot of similarity with logistic regression, as you're going to see in a minute. And the perceptron was then further developed in the 60s into multi-layer perceptrons, which are the foundation for what we know today as artificial neural networks. And now, while the multi-layer perceptron is not as complex as modern architectures, it's still interesting to take a look at this architecture of multi-layer perceptrons. And then in the course of the semester, we're going to take a look at ever more increasingly complex neural network architectures. And now, without further ado, let's jump into the theoretical background of the perceptron. So let's do a quick recap of the binary classification problem, because that's the problem we're trying to solve with the perceptron. So we have data x with data points x1 to xn from a real vector space, and we have corresponding labels yi to yn, which are binary, so they can be either 0 or 1. And what we can do now is we split our data x into a positive data set p and a negative data set n, with p containing all the data points for which the corresponding label is 1, and the negative data set containing all the data points for which the label is 0. So this might look somewhat like here, where we have our negative data points, our positive data points in the space. So this is for R2. in this case. And now the question to you guys is, how can we separate the data points? Tim, I'm sure you already know this.
Well, you know, in the 20 or so test runs of this video, I raised my hand and said, "Hey, I know how it is," but now I wasn't. But if you think back, maybe to the third, I think it was the third lecture, when we introduced you to linear and logistic regression, that was exactly what we did, right? So we had binary labels, and we separated those data points with a line. Exactly.
Yeah, exactly. So yeah, that's precisely what we are also going to do in this case. I mean, just the simplest solution, draw a line separating our negative data points and our positive data points. And yeah, as you remember, this hyperplane can be described with our hyperplane equation. And well, then we just translate this into the logistic regression problem where we build a classifier that that satisfies this equation, where this is the sigmoid function. But for the perceptron, we're doing this a bit differently. I mean, it looks very similar, but a little bit different. So instead of using the sigmoid function, here we're using the Heaviside step function. So this difference, again, stems back to the logistic regression and perceptron being developed roughly at the same time. And so basically here, the only difference is that in the perceptron, we have a step-like activation. So basically when our data point is in this half of the space, we output a 1. When it's in this half of the space, we output a 0. All right, so this is nothing that you haven't already seen. Now the question is, how do we find our vector W that is going to give us the, well, basically the optimal logistic regression? And this is where we start having differences between logistic regression and, or fundamental differences between logistic regression and perceptron training. So remember, for logistic regression, we did a gradient descent. Here we proceed a bit differently. So there's this pocket perceptron training algorithm, which works somewhat like this. So first of all, we need to choose an initialization for vector W. And well, what is a reasonable initialization? So a good initialization is to choose a W that looks similar to our other positive data points, because we want the orthogonal projection of our W with our positive data points to be positive, and we want the orthogonal projection of our W with the negative data points to be negative, so we can have a proper splitting of our space. And so what we do is we set the W initially to the average of all these data points, and then we can expect our W to have a similar orientation in space as all those positive vectors. So then we use an iterative procedure, and every step we select a random vector from our N union P, so from all data points in our data set. And then we have 4 different cases. So the first case, we have drawn a positive point from our data set. So this V, for example, and the scalar product of our W with our V is larger than 0. Well, in that case, we just continue. We don't need to do anything because our W already looks similar to a V's. So it already has the correct orientation in space, and the scalar product with that representative V of our positive data is already going to be correctly classified. Then there's the case where we draw a positive data point and the scalar product is negative, is smaller or equal to 0. So in that case, obviously we need to do some correction because, well, our V is pointing up here and our W is pointing down here. So the orthogonal projection is going to be negative. And what we want to do here is we want to shift our W in the direction of the V. So this is actually fairly similar to Oya's algorithm, if you remember that. So what we do is we add our vector v on top of the w and end up with a new vector v, w prime, sorry. And the negative case is basically just the same, only inverted. So we draw a negative sample, orthogonal projection is smaller than than 0, sorry. So in that case, everything is fine. And in the other case, well, we need to update. So in the other case, we need to shift our vector w away from the v. So what we do is we subtract our v from the w and we shift the w away from the v. And we repeat this until the updates become smaller than a given theta, so than a given threshold. So we assume that eventually this is going to converge. And in fact, one can show that this algorithm eventually converges if the data is linearly separable.
Luis, I have a question. So in Oya's algorithm that we introduced as like a preliminary kind of game, or game of thought, let's say, in the PCA lecture, we had a learning rate. So, right, so the update to the vector W was scaled by some learning rate. I think we used gamma or nu or something. And do we use a learning rate here too? Or can we use a learning rate here too?
I mean, in this case, we're not using learning rate, so in this formulation of the algorithm, but I mean, there's nothing telling us that we can't use a learning rate here, and we certainly could, right? Because, I mean, the point is, so if we use a learning rate on the v, I mean, the v is telling us how we update our vector. So what this would do is it's going to scale down our vector, and so what would happen here is that the shift of the w is going to be smaller than if it's going to be smaller or larger if we set a proper learning rate than just subtracting the unscaled v. So yeah, so basically this is definitely something which we can also do here. So we can set a learning rate which would simply be multiplied with our v, and this would tell us whether basically how strong our correction of the w needs to be. Yeah, so thanks for asking that question, Tim, because yeah, actually that's a very nice point here.
Luis, one question. So this data set looks, pretty simple. It's, one mass or one point cloud for the positives and one other point cloud for the negatives in exactly the opposite direction. So I wonder how this would work if, from the origin, you had two data set or two point clouds in almost the same direction, or even one point cloud here and then behind it, as seen from the origin, the other classes point cloud. And what about separability? So this algorithm seems to converge.
Yeah.
In the case of linear separability, but what if it is not? One data point is sufficient. If we put, for example, one red data point to this blue point cloud, then it's not separable. So what do we do?
I'm glad you asked that, Tim, because, well, I'm going to answer both of your questions now. So first, so your first question was, I guess, something like this, right? So yeah, so you have negative data points like this and our positive data points like this, and both are pointing in the same direction. And yeah, so in this case, obviously our algorithm does not work because we assume that the projections of our W or our orthogonal projections for the positive and for the negative data points are different. And in this case, well, obviously all orthogonal projections are going to be positive. So this doesn't work. And what we can do in this case is we just calculate the center of all the data points and we subtract it. And then we come up with something like this. And now, as you can see, everything is well behaved again. So if our W points in this direction, for example, our orthogonal projection with the positives, or our scalar product with the positives is going to be positive. With negatives, it's going to be negative. And everything works out nicely again. So we just calculate, so we implicitly calculate the support vector B before calculating the W in that case. And yeah, from there, it's just the same. Now, to address your second question, what happens if our data is not linearly separable? And is this even a problem? And well, yeah, it turns out this is a pretty big problem. And this is actually the reason why why there was for a long time, perceptron, people kind of lost hope on perceptrons. So if you look at the XOR function, which is a very simple binary function, and you try to come up with a boundary that separates the positives and the negatives, or the zeros and the ones in this case, you notice that it's not possible, right? You can tilt around your hyperplane however you want, but you're not going to find a hyperplane that separates your data. And well, this is obviously a pretty big problem. So this means that our perceptron is only going to work when we have data that is linear separable. And in fact, this is not only a problem with the perceptron, but as an extension is also a problem with logistic regression, because the only difference basically is that we are using a different activation function, so to say. So obviously this is a big problem that needs to be addressed. And well, the way that researchers found to work around this problem is to not use a single perceptron or a couple of perceptrons for multiple dimensions, but to use a so-called multi-layer perceptrons, which are actually they are what we today call artificial neural networks, or at least the precursors of modern artificial neural networks. And yeah, so now you've noticed we've already used several times in this lecture the term neural networks, but there's so far, yeah, Tim.
Before we go to
this,
sorry.
I see you want to help me out with this.
Well, I mean, before we move into the neural network part, I think I think the students would like to know. So if we still want to use perceptron, and we do have a data set that isn't XOR, because this is like a very simple yet unsolvable kind of problem, but still I think what we should share with them is like what do we do, what can we do if we had a linearly not separable data set. And if I remember correctly, reading on Wikipedia, we could use this the perceptron pocket algorithm stores solutions that are sufficiently good, so that have only a few data points misclassified, and then it returns these solutions, but we don't know when they or if they are actually reached or found, and we don't know. We have no guarantee after how many iterations or so we find these solutions. So I think there are a couple of variants that we will not cover here of the perceptron algorithm. And but yeah, so I just wanted to mention this, that it's not an algorithm that people have invented in the 50s and then have forgotten. I think people have been using this as also an inspiration, that led to support vector machines that we haven't yet covered. And there are many variants out there. had been used also on linearly not separable problems. And but now I'm going to shut up and leave you continue.
Okay. No, it's good that you pointed this out. I think actually some of those algorithms are fairly recent, from the 90s, I think. So max out perceptron, for example, I think it's from 1999 or something. So yeah, so there is a way how you can slightly maneuver around this linear separability problem, but the only way you can do this is basically by regularizing your problem and adding additional conditions, so your problem becomes a bit more well-behaved. But anyway,
use kernel functions, and then
yeah,
make your linear boundary more powerful, non-linear boundary, because you use kernels. But yeah, we will not touch this in this lecture, so let's move on.
Exactly. So let's move on to the connection that our perceptrons and our multilayer perceptrons have with neurons. And so I'm not going to bore you with a lot of biology here, so I'm just going to do a very rough sketch of how neurons, how biological neurons work. And so basically the idea is that your neuron is built something like this. So you have a soma, which is the body of the cell. You have the dendrites, which are connected to the terminals of other neurons and which get an input as a chemical signal. Then we have synaptic terminals, which are connected to the dendrites of other cells, in which produce an output of a chemical signal, and we have a transmission from the dendrites to the synaptic terminals over the axon using an electrical signal. And so the way these neurons work, more or less, or at least in the model, is we have an all or nothing rule. So if the incoming inputs are not sufficiently strong, we do not get an output response. And if on the other hand, the input signals are sufficiently strong, we do get an output response. And since our neuron is connected to several other neurons, what can happen, for example, is that we can have several input signals of neurons that add up or inhibit each other. And well, if again, we can have an insufficiently strong response or insufficiently strong input, or the signals can add up to create an output signal that travels down the axon. Okay, so let's put this biological model into a mathematical model now. So the idea is we have these inputs at the dendrites, right? And we're going to interpret the input from another neuron as a value x1 from the reals, and then we combine all those inputs into an input vector x1 to xn from a real vector space. And for the outputs, we do exactly the same thing. So for each synaptic terminal, we can model that as an output y1 to ym. So we have an output vector again from a real vector space. And then, well, logically, our outputs yi are going to be in some way proportional to the sum of our output signals. So basically, we just sum up all our inputs weighted with some weight wi. And well, finally, to model our all or nothing response, we can use our Heaviside step function. And now I think you already see that this is very similar to the perceptron. I mean, it is basically a perceptron now, right? So we had this Wx, our bias B, and we have our Heaviside activation function. And as an extension, it also looks like a logistic regression, only with Heaviside instead of a sigmoid. So what we can do now is we can model a single neuron as a perceptron with well, basically with multiple outputs. So this is what a normal perceptron would look like. Remember, we had only 0 or 1 as output in the normal perceptron. So yeah, so we have our inputs x1 to xn and our bias b. And well, all of these get summed up and weighted with the respective weights. Then we apply our Heaviside step function on top of that, and we get our output y. And now instead of having a single output in the normal perceptron, we modify the perceptron to have multiple outputs. So yeah, this looks pretty much the same as usual as earlier, only that only that now for each output we're going to have these connections from x1 to xn to our respective yi, and with the respective weights. And so this is just a graphical formalism thing. So instead of writing down the sum and the theta, since we are going to have this repeated expression anyway for all our yi's, we can just collapse this, and then we have this representation for the output.
Luis, maybe one thing that we should mention here, comparing this to the perceptron, where we had W transpose X plus B, so W being a vector and X being a vector. This becomes here W times X, and W is a matrix. And this is basically just, a bunch of vectors, W, now the rows of this W matrix. Yeah? And so it's basically the same as we've seen before with many units. Yeah. So the same graphical interpretation or geometrical interpretation holds as well, and each of these units now represent, let's say, different aspects of the data.
Exactly. I mean, so basically we're doing the exact, sorry.
Or respond to different directions of W. So of these units y, y1 through ym correspond to different vectors. So they have maximum activation if the input looks a little different.
Yeah.
Exactly. So similar to W.
Yeah, right. Yeah, so as you said, I mean, basically what we're doing here is we're just doing our WTX plus B, but for every single output dimension, right? So yeah, that would be the connection to logistic regression. And so for now, we have only done this. So we have only done this once, and right now we're not any better than logistic regression or the perceptron, except that we have multiple dimensions. So now we want to go in depth, so to speak. So what we want to do now is we want to model the architectures that we can also find out in the brain, where we don't just have two single neurons or don't have just one single neuron, but we have multiple neurons stacked in layers on top of each other. And the question, how do we translate this into our artificial neural networks? And well, the idea is, so previously we had just this single thing over here. So we have two layers. Oh, and by the way, this is something which is a bit confusing. So so our biological neuron basically is this whole thing over here. But when we talk about artificial neural networks, we call each single of these nodes a neuron. Okay, so this is a thing that is a bit confusing, but you get used to it eventually. Okay,
maybe we should add that the similarity of biological and artificial neural networks is really limited. So if you ask a computational neuroscientist or like a neurobiologist, you know, what he or she would think about artificial neural networks. So how much they are similar to biological networks. You know, you'll probably get a response that says, you know, it's a drastic simplification. And there's so much more going on, and so much that we don't really know yet. You know, it's the temporal dynamics, it's where the weights are, you know, so many different things, and also, so artificial networks nowadays are really highly optimized linear algebra, you know, operations. And we don't really need this kind of analogy, but you know, sometimes it helps to understand the history of things. And in the beginning of you know, ML, people like to think of software or programs or even computers as becoming intelligent. And then, of course, this analogy helped also to get funding or to convince the media, you know, that software machines are becoming intelligent.
For worse or for better, right? But actually, since you pointed this out, yeah, of course. So this connection between the biology and the actual neurons, of course, is very strongly restricted. But there's also some newer neuronal architectures like convolutional neural networks, which also have connections to biology, right? So I don't want to spoil too much in advance about that lecture, but basically what we see there is that there's also a connection from what's going on in the basically in the optical processing in the brain, in between what's going on in a convolutional neural network. So again, so again, there is a slim connection between the biology and the artificial neural networks, but you guys shouldn't take this connection at face value. So it's more of an analogy, and it's more of a source of inspiration from which we can draw ideas for machine learning. All right, so moving on then, unless you have anything else to comment on this. Okay, so what we're doing now is we want to increase the expressive power of what we've already built. So we want to go beyond a logistic regression with multiple dimensions, and we want to do this even better. And well, what we do is that instead of having just one layer after our inputs, we add another layer of artificial neurons behind our layer. And so this is something which this is the classical multi-layer perceptron architecture. So this is the most simple, sophisticated artificial neural network that you can think of, where you have a layer of inputs, you have an output layer, and in between you have a so-called hidden layer, which is called like that because the vector that we have here does not have any direct, so it's not from the output space. So it's basically in a so-called latent space that we cannot necessarily directly interpret. And so we call the neurons in this layer a hidden layer. Okay, and now what is...
Can I add something? Luis, sometimes you will find in the literature a network that you just showed or that is showing here, only 2 layers, because we only count the weight layers. So each of these connections here are weight matrices, W1 and W2, let's say. And so we would count this as a 2-layer network, but yeah, sometimes, you know, it's inconsistent And sometimes people count the layer of inputs, and sometimes they don't. So
yeah, exactly. It
don't
depends whether you count the neurons as layers or whether you count as the weights, the parameters. So what's actually interesting, actually. So you already mentioned these weight matrices W1 and W2, and I'm glad you did, because now the students are going to see how the mathematics of all of this plays out. So for the outputs of our hidden layer, basically everything looks like a logistic regression, only with more dimensions. I mean, so we have our input vector x from, let's say, double Rn, and now let's say our hidden layer has M1 neurons. So our vectors. So if we join all these neurons into a vector, it's going to be an M1 dimensional vector. And so our W1 is going to be an M1 times n dimensional matrix. Our bias vector is going to be an m-dimensional array or vector. And well, our Y1 is then W1x plus B1. And after that, we apply the Heaviside step function or a different activation function. We'll talk about this in a minute. Yeah, and we can also, this is actually a notation which you'll also find in a lot of papers. So sometimes this expression over here is summarized as Ci. And yeah, we end up with these terms. So again, so far, not a lot of new things, just a multidimensional logistic regression, so to speak.
The biases, Luis, they don't show up in your diagram here. But they usually show up as, and I think you did that on one of the previous slides. They sometimes show up as additional connection weights of an input that is 1.
Exactly. So again, I showed this in the first slide that I had on the perceptron, and so yeah, basically where the bias appears. So sometimes this bias is just implicitly assumed to be there, and you just draw the weight or the connections for the weight matrices. But if you insisted of having your bias represented graphically in this model, you would add an additional neuron here with value 1, and then you would have a connection with the value B of that bias to the neurons from the hidden layer. And then, of course, for the hidden layer, if you also wanted to have a bias added here, you would do the exactly same thing in the hidden layer, right? So so over here in the outputs Y2 from the output layer, everything looks basically the same as over here, only that we are at the second layer and not at the first layer. So basically all the 2's gets replaced with 1's. Sorry, the other way around. The 1's get replaced with 2's, and then everything looks pretty much the same. So now we have this matrix W2. And well, again, let's assume now that our output layer has M2 neurons, so M2 dimensional output vectors for our model. Then our matrix is M2 times M1 dimensional matrix or array, and our B2 as an M2 dimensional vector. And well, here again, we have the same expressions basically that we did earlier, only our 1 is counted up to 2. And here, instead of having the input X, we have the output from the hidden layer. And well, if we define our input X2 from the output layer to be the output Y1, then our equations look like this. Okay, and now we can simply repeat this for any arbitrary number of layers that we want, right? I mean, there's no reason we can only have just one single hidden layer in our network. We could just add as many hidden layers as we want, and we can generalize this equation that we have in the previous slide for any arbitrary layer L+1, depending on the previous layer L. So I hope the students do not get too confused by these equations, because all I've done here is I've replaced the 2's with L+1's and the 1's with L's. And then basically you already have the generalization for an arbitrary depth multi-layer perceptron.
Well, it's basically a vector, which is the input, times a matrix, and then push this through your Heaviside step function.
Exactly.
And then you have another vector. You know, it may have a different dimensionality than your X hat. But then you multiply this again with, you know, to a matrix and put this through this nonlinearity again. And this is repeated, and you just have to observe that the weight matrices match the respective dimensions.
Exactly. I mean, in a sense, this is just multidimensional logistic regression or multiple multidimensional logistic regression stacked on top of each other. So, right.
Well,
so
I mean, logistic regression would use the sigmoid function.
Exactly.
And so far we haven't yet told all of you that you could use that too, but so far we just used the step function.
I think I briefly mentioned it earlier, but I'm going to mention it again. And I think we're also going to see it in the next lecture, but it's good that you point this out briefly again. So now we know how to build a multi-layer perceptron, but we have claimed that this multi-layer perceptron is better than a single perceptron, but we still owe you a proof of this. And I think the best way of showing you this is by remembering the problem that we had earlier with our XOR function that could not be represented using a single perceptron. However, now if we use a multi-layer perceptron, we can actually represent the XOR function. And well, I do not expect you to, or at least I'm not going to go through the math of how we designed this, but if you have some free time on your hands in the Christmas holiday, you can go through this step by step and make sure that you understood how a multi-layer perceptron works, and you can verify that this multi-layer perceptron that I've sketched down here actually computes the XOR function. Okay, so now, as we already talked about just a minute ago, you don't have to use the Heaviside step function for your network. So there are other functions that you could use. So a typical choice, will be to use the sigmoid function instead of the Heaviside step function. And so particularly if you work with more advanced architectures like CNNs, there's also a bunch of other activation functions such as ReLUs that you can use, but I don't want to dig too deeply into that aspect. So what you need to know is that the activation function needs to be a nonlinear function. And the reason for this is that if we don't use a nonlinear function, so basically if we don't use any activation at all, but just an identity as activation, our network function, so the function that our entire network represents, is just an affine linear transformation. So in other words, our network is not going to be better than a linear regression. And the reason for this is that a concatenation of affine linear transformations is also an affine linear transformation. So in case you don't believe me, I've sketched down a brief proof of this, where we can also recap a bit of the formalism. He's smiling.
Are you going to read this now?
Well, I'm not going to read this, at least not all of it. So I'm just going to show you basically how the proof plays out. I mean, the idea is just you take the L+1th layer, use the definition of the L+1th layer, and then we insert for our activation function f our identity. So we just end up with this thing in here. And then for 2 layers, we do the same thing. So again, insert the definition for YL+1. Then we insert the definition for L+2, sorry. Then insert here the definition for YL+1. So that's the term over here. Then we separate this. And then you can see here we have a product of matrices, which is going to be a matrix. And here we have a product of our matrix with our bias, BL+1. And this is independent of input YL. So what do? We sum up our matrix product to a new matrix, and we sum up this expression, which is a vector, to a new bias vector. And then we end up with this, which is, well, just a single, basically what a single layer was already doing. And so we see that by using no activation functions, we have no gain from stacking multiple layers on top of each other.
I think the intuitive idea here is, you know, forget about, I think for a moment, forget about the math on the slide and just think of—
That's going to be hard for me.
I mean, you, the students.
Okay.
Yeah. So think of an input X and forget about the biases. We could, like in logistic regression, we could use an additional input dimension and an additional weight dimension. Yeah. So we could get rid of this plus B in these slides. But let's for a moment only think about X times W. Or write it like that. So the weight matrix W times X is the activation of the hidden layer without the nonlinearities. And then multiplying from the left, new matrices is basically adding layers of weights. And now you can just multiply all these matrices together and then multiply the X. Now you don't have to do it from the right, like W1 times X, and then this is a vector, and then you take W2 times this vector. No, you could, multiply all these matrices from the left, collapse these into one matrix, and then it's just one, whatever this matrix is, it is just a linear mapping from X to whatever output.
Yeah, right. So what you're basically saying is we do, so by collapsing our B, so our bias into the matrix and choosing that compact representation, we just end up with something like this. And now you can already see as we stack up more matrices here on the left, I mean, we just end up with a product of matrices again, right? So we can just collapse them into one single matrix. And yeah.
So bottom line is we need nonlinearities.
Exactly. That's the bottom line here. And yeah, and the other bottom line is that it's nice to, at least if we want to stack multiple layers. But now there's one interesting question. Do we actually need multiple hidden layers to have a good model?
How many do we need?
Yeah, how many do we need? And actually, in theory, you just need one single hidden layer to be able to model pretty much any function you want. So there's this universal representation theorem, which tells us that a shallow neural network, so with one single hidden layer, can approximate any function f given enough neurons of, so I simplified this a bit, but basically this is what the universal representation theorem tells us. And so then here there's a bit, a slightly more formal explanation of that theorem, which is also reduced, by the way. So the actual theorem is even more, slightly more complicated and uses more assumptions. But so a broken down mathematical way of saying this is that if we have a function from the reals to the reals, no matter what epsilon, so no matter what tolerance of the error we choose, we can find a number of neurons that is sufficiently high enough and corresponding weight matrices and biases such that our our prediction function of the network minus the actual or minus the function that we actually want to approximate is smaller than this epsilon. So in other words, the deviation of our predictor function from the desired function becomes smaller than any epsilon which we set if we choose a sufficiently high number of neurons.
That's the perfect example of when theory predicted something really nice, but empirically we had to wait, I don't know how many decades until I think in the 2010s, right. Deep learning lifted up. Before that, multi-layer perceptrons couldn't solve hard problems.
Yeah, true.
Solve in a way that is printed on this slide here.
Exactly.
So
yeah, basically the idea here is that although this is a nice theory, it really doesn't work out practically. And the reason for this is that even though we can try to minimize the error of our neural network with respect to that function we want to approximate, in theory, there is no easy way of doing this practically, because so the way we change our network, so the way we adapt our network to look like the desired function is we tune our weights and biases to end up with something that looks like our function. But how do we tune those weights and biases? And well, that's the tricky part. How do we come up with a good solution for our network? And this is the difficult part where the theory doesn't help us, because even though we know there might be a solution, we don't know how to find that solution. Or at least it's not straightforward to find that solution. So this is where the learning part comes in. So, so the basic idea here, like for most models, which we have talked about in the lecture, would be we choose some loss function L, then we have our set of all network parameters, data X and targets Y, and then we try to minimize the loss of that function with respect to our weight. But how do we actually do that? So remember we had this concept about gradient descent in logistic regression. Now, the network here is basically a lot of multidimensional logistic regressions stacked on top of each other. So you might get the idea, okay, we used gradient descent in logistic regression, why not use it here? And well, yeah, you can actually do that. So you can just compute the gradients of your loss function with respect to the weights, at least in theory, and set them to 0. And then you can use gradient descent to find your minimum. But so, if you remember logistic regression, those expressions which we had were difficult enough, and the derivation of the gradients for logistic regression is not very straightforward. Now, we don't have just one layer of weights, but we have a lot of layers of weights stacked on top of each other. So how the heck are we going to derive, you know, an explicit expression of the gradients for all those weights?
You watch the next video. That's the answer.
Exactly, that's the answer. So I hope you're not too mad at us for leaving you with this horrible cliffhanger over the Christmas vacations. But so to find out how you optimize the networks to end up with good predictor functions, I'm afraid you're going to have to watch the next video. So yeah,
That's it.
Sorry?
That's it already. That's a short one.
Huh?
That was a short one. I thought it was longer.
You mean the video or the lecture?
Yeah.
Yeah. I also expected it to be a bit longer, but yeah, it worked out smoothly in the end. So yeah.
So what about the assignments? The students should probably implement the Perceptron learning algorithm, don't they?
Yeah, I think that's probably a good idea. So I think the best thing would be for the students to first implement just a perceptron with no, sorry, not a perceptron, but to implement a multi-layer perceptron where they can stack multiple layers on top of each other, and then in the assignment for the second part of the lecture, they will have to use that MLP that they implemented to learn some some function. What do you think?
Yeah, so we could use this assignment as a preliminary build-up to then implementing backprop.
Yeah.
In the next assignment.
Exactly.
Yeah. Okay, sounds good.
All right.
We should also look at, you know, there has been progress on non-backprop based learning in networks. Maybe we should touch this too. I should have.
Good point.
What's it called? Well, anyway, let's just finish the video, and while the students are watching it, we can prepare the new lecture.
Yeah.
Yay!
Let's start right now.
Right now, I'm on it. I'm on it.
Okay, great. All right. So I hope the students were able to follow the lecture. I hope you guys aren't very confused, and I hope you will remember enough of this to be able to follow the lecture after the Christmas holidays. For now, thanks for watching. Have great
Merry Christmas.
Merry Christmas, Happy New Year, and we'll see you in the next year. Bye.
Stay safe. Bye.